All right, so congratulations. We've made it past determinate structures, and finally we get to deal with indeterminate structures. And we're going to introduce today the flexibility method, which is one of the most fundamental methods for solving indeterminate structures. And I like it because it is very intuitive to apply, as we'll see. But the study of indeterminate structures is important because it opens up our abilities to deal with a much wider range of structures. So let's look at that in the big picture. So here's Camden Bridge, which is what we would call a continuous girder bridge. So take a moment, pause the video, and try to see if you can idealize this bridge as simply as you can. Okay, so here's how I would do it. We have clearly a single beam for the entire bridge. These connections are full connections, so they're transferring moment and shear and everything across them. So you can treat it as a single beam. And then we have obviously these supports, which look to be pins. Okay, so I would start with this approach, and obviously we have to consider the abutments as well on either side, and those probably would be pinned or fixed. Let's go with pinned. And so we would get a continuous beam with 2 pins for the abutments and 3 pins for the piers. Okay? Now we can simplify this further by saying that, or by observing that the loads are mainly going to be vertical. And so we can assume that any sort of horizontal reactions are going to be negligible, and simplify this further. So I'm going to turn every pin into a roller except for one, so that we have at least a stable structure. All right, and so that's about as far as we can go in simplifying this structure. And this is really what we would call a continuous beam. Sometimes you might see it with all rollers, but is essentially a beam supported at certain intervals by rollers. This presents a problem because obviously if we want to solve for the reactions at those rollers, we only have 3 equations. And so we would need, in this case, with 6 reactions, we would need an additional 3 equations. And so this is a classic indeterminate structure. The way to get those equations is by observing that there are additional constraints placed on the beam by those new supports that we add. So to get a determinate system, all we would really need is, let's say, the pin and the roller here. So that's enough for a determinate system. The additional rollers essentially place constraints on the deflection such that those points must be 0 deflection. So that's where our 3 additional equations come from, and that's exactly what we'll take advantage of in the flexibility method. So the objectives for today are to take a big picture look at indeterminate structures and talk about their advantages and disadvantages and why you might want to use them in certain cases. Then we'll introduce concepts of redundant supports and compatibility, which is that idea I just brought up about additional constraints on the structure. And then finally, we'll describe the general procedure for the flexibility method, which is based heavily on the principle of virtual work. And we'll apply it to just first-degree indeterminate beams. So let's talk about first the advantages of indeterminate structures. One of the big advantages is that they generate smaller stresses. So if we compare side by side a simply supported beam with a fixed beam on the right side, clearly the fixed beam is an indeterminate structure. It's got 6 reactions. And so if we look at those two and plot the moment diagrams for both, we know how to do it for the indeterminate structure. It would simply look something like this. Okay, so let's call this the maximum bending moment. Let's call this M max SD for statically determinate. Then on the other side, the moment diagram, which we do not know how to solve for yet, would look something like this. You would actually have end moments, so you would have jumps at those supports, and so you would get something along those lines. So essentially what happens is the parabola shifts up by those end moments. So what this does is this reduces the overall maximum moment. So we have that M max for the statically determinate structure is greater than M max for the statically indeterminate structure. Okay, and obviously moments are proportional to stresses, therefore also the induced stresses are smaller. The overall takeaway is that loads can also be larger, right? So for the same span, the same beam can take more load if it's supported as a statically indeterminate beam. So this gives us an advantage in terms of the overall strength of the structure. The beam can sustain more load by adding redundant supports. However, of course, the supports are going to now take more of that load, so we have to keep that in mind. A second advantage is in terms of serviceability, in terms of the deflections that the structure undergoes. So indeterminate structures also have greater stiffness, which means lower deflections. Let's look at what the deflected shapes would look like for both of these. For a determinate structure, the beam can angle on the support, so that it will actually allow it to sag down quite a bit, as we will see. And we'll call this deflection delta SD. For the indeterminate beam, the ends actually have to be at right angles, right? We know that. And so the overall deflection will be significantly less. We'll call this delta SI. So the takeaway here is that delta SD is greater than delta SI. Okay, so not only do we reduce the stresses, but we also make the structure stiffer, it deflects less by, again, virtue of those supports constraining the deflection of the structure more than the statically determinate system. And the final advantage is the fact that we do have redundancies against failure. Okay, so by redundancies, all we mean is additional supports. All right, so on the left, if we have a statically determinate structure, right here we have 4 reactions, but we have a hinge, so it's overall statically determinate. And the middle support fails, there's really nothing keeping that structure stable, right? So the structure has now become unstable, and so it will fail. On the other hand, the statically indeterminate structure has redundancy. So in this case, the hinge has been removed, so this is statically indeterminate by 1 degree. So if I remove one support, the structure will deflect more. So now it's a determinate structure, but it still will stay stable. Right? So we've gone from a statically indeterminate by degree 1 to a statically determinate structure. So therefore, we have a little bit of more, let's say, built-in redundancy, built-in kind of safeguard against potential failures anywhere in the structure. Now let's talk about the disadvantages of indeterminate structures, or you could think of this as the advantages of determinate structures. One of those is the stresses due to support settlement. So as we discussed in the principle of virtual work section, determinate structures, if the supports move, they simply just rearrange themselves around the new support without introducing any sort of new loads on the structure, right? Because they're determinate, they adjust to the support conditions. So let's take the example of the same beam as before. It's got a hinge supported by a roller. That roller settles down. Simply, the hinge will just drop with the roller, but the beams connected to it will remain straight. They'll simply rotate around the hinge. The important thing to notice is because those are straight, that implies that the moment in these beams is zero, just like it was in the original configuration. So no new loads, no new stresses have developed. On the other hand, for indeterminate structure, when that support goes down, that pulls the beam down with it, right? So that introduces a curvature there, and so moment is not zero. In a similar way, other stresses can develop from changes in temperature or fabrication errors, right? So anything that introduces kind of geometric changes to the structure will generally cause more problems for indeterminate structures. So if the determinate structure heats up and expands, then it will simply just expand with that roller. The roller will be able to accommodate the expansion. On the other hand, if the indeterminate structure wants to expand due to a change in increase in temperature, what will essentially happen is that it will start to compress. So we'll introduce a compressive force into the beam. Okay, whereas in the other one, there was no force. Now let's be clear here, we're talking about positive temperature changes. Okay, so now it's where we get a little more technical. So in order to analyze indeterminate structures, like we mentioned, we need additional equations. So it's worth taking a step back and thinking about all the different types of equations and conditions that need to be met whenever we're dealing with forces and deflections. So any structure, whether it's indeterminate or determinate, must satisfy three types of relationships. Sometimes we don't need to use all these relationships to find the loading, internal loading, but in some cases we do. Okay, so the first set of equations we already know. They're the equilibrium equations, which we've been using a lot. Okay, and obviously those relate the forces on the structure. Right, so all loads must balance. That includes the external loads, the reactions, and the internal loads in the structure. The second set of equations or relationships that need to be satisfied is what we call compatibility conditions. This relates displacements in the sense that the structure cannot suddenly break apart at a particular point, right? So joints need to remain connected and everything needs to remain connected. And on top of that, the support conditions need to be satisfied. So any constraints imposed by the supports, such as let's say a fixed support, right? The angle at that fixed support must remain 90 degrees, right? So we can use that as an enforcing equation to give us an extra bit of information. And the final one is the force displacement relationships. Alternatively, you could think about this as moment angle relationships or moment rotation relationships, right? These are basically what we used in the principle of virtual work, right? That depending on the internal loads in a structure, it must deflect in a certain way, right? So there's a direct one-to-one relationship between internal loads and deflections of the members. And that all really comes down to stress-strain relationships. So in the flexibility method, we'll make full use of the compatibility conditions number 2 to set up additional equations, but in using the principle of virtual work, we'll also take advantage of number 3, which are the force displacement relationships. So then let's introduce the general procedure for the flexibility method using the continuous beam as our first example. So the first thing you need to do is to determine the degree of indeterminacy of your structure. So in this case, we have a beam, so our basic equation, remember, is 3m plus r equals 3j plus ec. Solving that out, we get 10 is greater than 9%. primarily because we have that one extra reaction, right? And so our degree of indeterminacy then is 1. This means that we have one extra reaction, okay, or a redundant, as we call it. Okay, so we just need to choose what reaction we're going to treat as redundant, and this is an arbitrary choice. It's up to you. But I think to keep it the simplest possible, we should choose B as a redundant. That way we go to our basic simply supported beam, right? So B will be our redundant or extra reaction. So in essence, if we can determine the reaction at B, By, then we can use equilibrium equations to solve for the remaining reactions. The second step is to remove the redundant and establish a compatibility equation. All right, so we've chosen B as our redundant. So we'll go ahead and remove that to establish what we call our primary structure, which should be statically determinate. All right, this is very important. In this case, since we have 1 degree of indeterminacy structure, we only need to remove 1, but we may need to remove more in other cases. So after removing B, we get the following primary structure: pinned at A and roller supported at C. So the deflection of this structure in response to load would be something like this. So in fact, B would deflect down, right? But we know that in the real structure, B is not going to move, right? The deflected shape would look something like this. So the compatibility equation that we're after is that delta B there should be equal to 0. So step 3 is really the main strategy of the flexibility method. And it uses both the primary structure and the principle of superposition to essentially impose the compatibility condition that we're after. So if we look at our full structure, right, our indeterminate structure, the expected deflection would be something like this, again. And the compatibility equation that we're after is that delta B equals 0. So essentially we can treat this full structure as the superposition of our primary structure with the normal loading condition, which we'll call our 0 structure, okay, plus the primary structure loaded by the reaction force. So in this case, By. So because it's loaded at B, I'll call this the B structure. Remember, because you might have multiple redundants, you could have multiple primary structures loaded at different locations according to those redundants. Okay, so what we're saying is that the 0 structure will deflect down in this way with a deflection delta B0. And the B structure will deflect up with a deflection delta BB. It stands for the B structure being loaded at B. So the compatibility equation that we want to enforce is that By should be a value such that, right? So we get to define By such that delta BB cancels out delta B0. Okay, so in order to do that, we'll actually slightly change our definition of that B structure to make things a little bit easier. So again, we have our real structure equal to our 0 structure plus our B structure. But in this case, I'm going to define my B structure a little more generally. Instead of setting By to an arbitrary value, I'm going to set it to 1. similarly to the way we did principle of virtual work. And I'm going to call the displacement resulting from that unit force, I'm going to call that FBB. Okay? By doing this, essentially what we're doing is we're saying that we can scale that unit force by any value we want to get the resulting FBB that we want, right? So it's just a simpler way of doing math. So our compatibility equation changes to delta B is equal to delta B0 plus By times FBB, right? And that should be equal to 0. Right? And By times FBB is our delta BB, right? So by solving that B structure for a unit force, we can simply scale the resulting displacement by any force that we want. So we can use this equation to solve directly for By if we know FBB. So we need to determine first B0, delta B0, sorry. That we will do using principle of virtual work. Should be obvious that that is a determinate structure which we can apply principle of virtual work to. Then we need to determine FBB, which we can also do using principle of virtual work. Keep in mind that in this case, the B structure is not your virtual system, right? It will have a virtual system of its own, right? So it's important not to get that confused, even though we're using a unit force here. It's not a virtual system. So these will be two separate applications of the principle of virtual work. There will be essentially two real systems with corresponding virtual systems. And then finally, we need to determine By using the equation. I should be explicit here and say that FBB is defined in terms of displacement units over force units, which makes it applicable to this equation. So essentially, we divide out by that 1 to get FBB. Okay, so let's go ahead and follow those 3 steps. First, we need to compute delta B0. Okay, and like I said, this is its own real system plus virtual system problem. So the real system is, of course, our primary or our 0 structure, okay, for which we want delta B0, of course. Our virtual system will be essentially identical to our B system, right? Because of the nature of this problem. So I'm going to go ahead and apply the virtual force up just to make it exactly identical, because then we can take advantage of it in the next step, right, when it's our real system. So this virtual system will look like this, and because we have a discontinuous force, we need 2 sections. So I'll define a section 1 there with variable x. Actually, let's call that x1, and then I'll define another section S2 with variable x2. And therefore, I need to do the same thing on the real system. Okay, in order to use these sections, we'll need to solve for the reactions. So I'll go ahead and give those to you. So for the real system, they're equal to 24 kips, both of them. For the virtual system, they're equal to -1/2, each of them. All right, so to focus on the method, we won't spend a lot of time on applying principle of virtual work. I'll just give you the solutions, and if you want, you can make sure that you can obtain them. So for section 1, in the real system, you would get the moment 1 is equal to 24x1 minus 2x1 squared. And for section 2, you would get 24x2 minus 2x2 squared. So essentially, same thing. And for the virtual system, you would get the following. So applying virtual work to solve for delta B0, we get the following. And solving out this integral, we get the final result that delta V0 is 1080 over EI. Okay, so let's leave that there. Now we move into step 2 of this process. We have to do another virtual work computation for FBB. So our real system is our B structure. So that's the following. And our virtual system, coincidentally, is the same system, right? Because of the way we defined it. This is generally true for the flexibility method when you're solving for 1 degree of indeterminacy. Is not always true for more than 1 degree of indeterminacy. So don't think that this is a default. It's just for single degree of indeterminacy systems. All right, so we know the solutions to both of these, so let's put those up. And again, let's just make the sections explicit on these. And finally, we solve the virtual work equation to get FBB. Notice how my virtual work PV is defined over here, and my FBB is the displacement of my B structure. Okay, so solving that integral, I would get FBB equal to 36 over EI. And this would be technically in units of displacements, but we'll treat it as units of displacements over force. So feet over kips. Okay, so in order to explain why we do that, let me take a little tangent in purple here. All right, so when we do this, really what we're solving for is a delta BB here. And we can call the force being applied, the unit force, big F B. Okay, so really what we're solving in terms of principle of virtual work is PV times delta BB, okay, equals so on. So we solve for delta BB, and then we say that FBB is really equal to delta BB divided by that force FB, right? What we're looking for is the resulting displacement from a unit force, right? That way we can multiply by any unit force to get the resulting displacement. But because basically this FBB is always equal to 1, we essentially just kind of fudge this and say that they're both equal, and we just change the units. All right, so we're kind of abusing the FBB notation here, but that's the way it's been done, so that's the way we'll stick with it. And so our last step is to compute By, and this is actually pretty simple. We start with the compatibility equation that we defined a little while back, right? And we know delta B0, we know FBB, so we can rearrange this to solve for By. And so we get negative delta B0 over FBB, and that is equal to negative 1080 over EI divided by 36 over EI. That gives us 30 kips. Okay, so our By is a 30 kip force. And now that we have By, we can use basic equilibrium equations to get our remaining reactions. So it should be obvious that Ax is equal to 0. And then from symmetry, we also get that Ay and Cy are equal, and those are equal to 9 kips. Yeah, you can use both moments and sum of forces in the y to get those. All right, so given that, we can then solve for the shear and moment diagrams in the same way that we've always done. So let's plug in those reactions here. 9 kips, and so our shear would look like this. right? Jump up at 9 at AY, then a jump up of 30 at B, and then another jump up at C. Okay, so same rules apply, and of course same rules apply to the moment diagram as well. And so the shape would look like this, with peaks at 10.125, right, which you would get from integrating this area here. You would get inflection points here, and your bottom maximum moment would be negative 17.875, which again you would get from integrating the total area on that side, right? And so from those inflection points, we can draw perhaps a better deflected shape, right? So we know that these are positive curvatures, these are negative curvatures, so we have positive curvature here, inflection, then another inflection and positive curvature again. Okay, so that's our lesson for today. As you can see, the flexibility method is a simple method for approaching indeterminate structures based on imposing compatibility. It is best if you use it for structures of degree of indeterminacy 1, 2, maybe 3, but it gets exponentially harder as you apply it, as we'll see. We'll apply it to 2 degree of indeterminacy 2 structures, and you will see that it gets increasingly more difficult. So it's good for low degree of indeterminacy problems. And it requires at least some method of calculating displacements. We've only learned virtual work, so that's what we'll use, but you should be marginally or peripherally aware that there are other methods out there, including moment area, direct integration, and Castigliano's theorem. So for the next class, we'll look at more examples, and we'll also apply the flexibility method to frames. So give a shot at some of the examples in the example PDF, and I'll see you on Thursday.